The counterpart of an electric dipole is a magnetic dipole. And in the last session, we talked about a very short electric dipole as an antenna. In this session 16.3, we're going to talk about a very small magnetic dipole as an antenna. So imagine that in space, you have a very small current loop, and this current loop is sitting at the origin of the coordinate. And there's a current running on this current loop given by this expression. There's an amplitude I multiplying with the cosine omega t. So this is the harmonic current. And we want to know the radiation field, a distance r from this current loop. And this r is much larger than the radiation wavelength. Because this is the magnetic dipole, so we can also write down the expression of the dipole moment, which is the current multiplying with the area of this current loop, given by this symbol m. And we're going to use this symbol m in our derivation. So let's go through the step 1, step 2, and step 3 to calculate the electric field and magnetic field. So initially you have a current loop. So you can calculate the vector potential at location of r, and then you use this expression to calculate the magnetic field. Once you have the magnetic field, then you use the Ampere's law to derive the electric field. The final result in the far field zone is given by this expression and this expression. So the dominant field component are phi component of the electric field and H component of the magnetic field. If you compare these two field components with the field component derived from the Hertzian dipole, you see that along phi direction for the magnetic dipole is very similar to the phi component of the magnetic field derived from the Hertzian dipole. And the H field, magnetic field along theta direction for the magnetic dipole antenna is very similar to the theta component of the electric field derived for the Hertzian dipole. Also, you can see that the field components are sort of orthogonal to each other for these two cases. For example, the phi component of the electric field is dominant for the magnetic dipole antenna, but the theta component of the electric field is dominant for the Hertzian dipole antenna. So the expressions are very similar because you can see the same dependence of the theta in this case and also in this case, and also the 1/r dependence in this case and also in this case. But the field in these two cases are orthogonal to each other. So once we have the field components for the magnetic dipole antenna, we can calculate the average power density by writing this complex Poynting vector. And you can finally have this expression for the power per unit area for this magnetic dipole antenna. Again, you see this sine square theta dependence in this average power flow along r direction. And you also see the 1/r squared dependence from this S expression. So if you do surface integration about a sphere with the antenna at the center of the origin, then you can have the total radiation power, which is independent of the location, because if you have a cross surface at any location about this antenna, the total power incurred should be a constant due to the energy conservation. So this is the same result you have for this magnetic dipole antenna. And also from this sine squared theta dependence, you can plot the radiation intensity pattern of this antenna. Turns out that this pattern is the same as the one we have for the electric dipole antenna. So you can also plot the E-plane pattern and also the H-plane pattern. And from those two patterns, you can conclude that along the dipole axis, you don't have radiation. And along the direction perpendicular to the dipole axis, you have the maximum radiation. Also, because the whole system is symmetric about this dipole axis, therefore you have this circle in the H-plane pattern. 所以在这一节里头呢，我们很快的计算了一下这个磁偶极天线的一些特性，结果呢，它的特性非常类似电偶极天线，也就是说，在原场的地方，这个它们的这个场呢，磁偶极天线跟电偶极天线的场呢，其实是这个形式是类似的，但是呢，要注意到的就是它们的电场跟磁场呢的方向呢，是互相垂直的。也就是如果说这个电偶极的电场是在这个方向的话，磁偶极天线的这个电场呢会是这个垂直的方向上头。那在原场的这个部分呢，它的 radiation pattern 也是一样甜甜圈的一个形状。这表示说，即使是磁偶极天线呢，它的沿着偶极方向呢，它的辐射还是0，但是垂直于它的这个dipole axis 的方向呢，会是最强，所以这是磁偶极天线计算里头得到了这个结论，非常类似电偶极天线的这个结果谢谢。